Yeah, let's talk about gravity some more. Do you need to write that down? Spelsky, put the phone away. So tired of phones, you guys. You know what? I used to be the teacher that said, no, we need to teach the kids when and when not to, but I'm slowly thinking maybe we should just check them at the door. Seriously, you guys, you gotta put them away. Anyways, so during the Great Plague of 1665, the bubonic plague, the Black Death that was sweeping through Europe, right? You guys think you've got it tough. Isaac Newton was at college, they evacuated, they sent people home because of the bubonic plague. So he was at home doing nothing, right? And he began thinking about gravity because he's a smart guy, right? A century before him, a guy by the name of Johann Kepler developed laws to explain the motion of the planets. They are still taught to this day. I teach it in grade 12 when I get to that unit. And Newton wondered if the same force caused an apple to fall to the ground from a tree. Do you think Newton was really sitting in an apple orchard and a tree hit him, or an apple hit him in the head? Unlikely. They think that he was actually walking one day, saw an apple fall. The moon, you know how you see the moon in the daytime as it went across the sky, and he got thinking, I wonder if what causes the apple to fall is the same thing that causes the moon to fall. And is it? Kind of. Kind of. This led him, Bob, yada, 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 do some maths, physics. This led him to the law of universal gravitation. When I say universal, it means true everywhere. And everywhere means everywhere, the universe. And it says, don't write this down. You don't need to know. Well, yeah, maybe you do. Yeah, you should know. Between every two objects there exists a force of attraction. You know that already. Right? You should. Between every two objects there exists a force of attraction. And this force is proportional to the product of their masses and inversely proportional to the square of the distance between their centers. I'll explain that in a second. When I say the region around a mass which the second mass which brings the gravitational force is described as a gravitational field, what I mean is I have a gravitational field, I have a mass. My marker is a second mass. It's close enough to experience a gravitational force. This region around me is known as a gravitational field. Brendan, do you have a gravitational field? Yes, he does. Will has a gravitational field. Everyone in the room does. Some have bigger gravitational fields than others. Who are those people? Not names. The bigger people, right? People with a larger mass have a larger gravitational field. Without trying to pick on Josh, Josh likely has the biggest gravitational field in the room. How's that feel, Josh? Yeah, you can strut down the street knowing you got a big gravitational field? Nerd. People say that like it's an insult. The strength of the field, just listen, let me read it and explain it first. And then when you write it down, you'll get it better. Okay, ladies, the joke's over. I know it is. Most of what I say is fine. The strength of the field at any place is defined as the gravitational force that a unit mass, 1 kilogram, would experience if placed there. Don't write it down yet. Hang on. Here's a 1 kilogram mass. This happens here. I'm going to put it in Josh's gravitational field. What kind of force does it experience? Just sitting there. All right. You're not that big. How come? Is there a force though? Absolutely, but it didn't move because it's negligible. Josh isn't that big. I crushed him. Yes, I'm sorry. The strength of the field at any place is defined as the gravitational force that a unit mass, a 1 kilogram mass, would experience if placed there. In this case, it was very small. Now, could I actually calculate it? You know what? Just for fun, Josh, do you mind? I've started picking on you. I might as well go right to the max. Do you mind if we weigh you? No. You don't mind? Okay. Okay, yeah. Now here we go with the conversation. Does this diagram imply that gravity is weaker as you climb in altitude? As you go farther away from the surface of the Earth, that gravity is weaker? Yes. Technically, theoretically, gravity is weaker here on the second floor than it is on the main floor. In fact, we weigh less. You go right ahead and plug into me. It's kind of hot, isn't it?
It is so hot in here.
So, this diagram tells us that as you go in altitude, gravity decreases in strength, right? Okay, so let's just move on from that. Okay, so if you were to draw a graph of gravity at different altitudes, what would it look like? As you went up in altitude to the right, across the bottom, right? What would be, it would go down, right, Dan? Would it be a straight line or would it be curved, do you think? Why do you say curved? Don't know, just got a feeling? I know it's curved, well, because I know what the slide looks like, but I know it's curved because, oh, let's go back. You know, it's r squared. It's a squared, it's an inverse squared. A lot of things are inverse squared. Things that decrease in strength as they get farther away are inverse squared. Come on, go to the next slide. Okay? Sound is another one. Whoa. Now it's not going to want to go back. Okay. Sound is another one. Magnetic field strength. A lot of things, as they spread out, decrease in strength. And they follow the inverse square law. So, you would actually get a graph that's like this, right? Here's at Earth, at 0, right? It's about 9.8. Notice that at an altitude of 400 kilometers, do you not have a door? Oh.
I want to learn about gravity.
Okay. Well, you know what I used to say about gravity? Set you up like that? He wasn't paying attention in class either.
One thing I remember from physics, the flying pig and that North Pole moving because the penguins and polar bears team up and pushing.
Hurtful.
At least I remember that.
I didn't even teach you about the polar bears and penguins. It's just like every day. Yeah, Smigalski too. Mr. Dick was in school. I never taught him. He was in school when I first started. All right. So notice from the graph, that just means I'm wise, right? Thank you. Tell me A+ for you. Notice that at an altitude of 400 kilometers, here's the important part, you guys. Had our little fun. Here's the important part. Notice that at an altitude of about 400 kilometers, gravity still pulls at about 9.5 newtons per kilogram. Gravity, up there where the International Space Station is, where Howard Wolowitz was up to his pranks, right? Gravity is still 9.5 newtons per kilogram. I thought space shuttle astronauts were weightless. You've seen the video of them floating around, right? How do they do that when gravity is 9.5? Like, really? Is 9.5 that small? What is going on here? Is it all a hoax? No. Inside the shuttle, inside the space station, there's air. Here's the deal. This is the part you need to know. Put your pens down and just listen. Here's the part you got to know. The space shuttle astronauts and anything else in orbit. What other kind of things are in orbit, Braden? Satellites? Anything else? The moon is orbiting, that's true.
We're orbiting.
Are we, like humans, you mean? Oh, we're not orbiting the moon. We're orbiting the sun, right? But anything else that is orbiting Earth are actually, here it is, falling forever. Forever falling? I don't know. There's a reason I don't teach English or art. They are actually falling forever. They just never land. How come? Because the shuttle is traveling at a great horizontal speed. Just watch and understand. I'll give you a chance to write down if you want, okay? So, here's Earth, right? Here's the velocity horizontal. It's moving sideways, right? Here's the vertical velocity because it's falling, and when you add those two vectors together, what do you get? You get that one. And the same thing happens over here. You get this one and that one, and it goes like this. And then down here, you get this one and this one. It's still, right here, it's literally falling, but still going forward. And so what does it do? It keeps falling and going forward. When I take the tennis ball out and throw it, Alex, I'm throwing it at you. Did it curve? A little bit, right? And if I threw it faster, I'm going to throw it right here, okay? No, other side, right? If I throw it faster, did it curve as much? He's got great hands. I knew that. That's why I picked it. Right? It doesn't fall as fast, right? If I throw it really fast, you can put your hand up. So I've got a target, yeah. Right? Hardly fell at all. Sure, you say he's got great hands, but no one said nice throws. I'm actually surprised I can do that. Okay, now I'm going to throw it really not so hard, right? What does it do? Oh, sorry. That's, yeah, a good arm. Exactly, right? Okay, but now, if I could throw it, if I could really hum it, right? Like wind up and throw it as hard as well. Okay? Meters per second. Right? If I could throw it hard enough to match the curvature of the Earth, what would happen? Well, it would fall with the curvature, and it would never actually land. How fast do you think I have to throw it at this height? I did figure this out once. I am a real nerd. I figured out roughly that you'd have to throw it from about here to the Country Fest site in less than a second to match the curvature of the Earth. Yeah. And that would be assuming that the Earth is perfectly round and there's nothing in the way either, right? So, not going to happen. So that's what happens, okay? Now, when you're in free fall, can you let me just put that back there. When you're in free fall, can you actually measure your weight? Like imagine I strap the scale to my feet and I jump out of a plane. What's it going to read?
Well, how hard is the strap to your feet?
Okay, it's not like really, really tight. Like it's just strapped to my feet. It would weigh 0, would it not? Okay, because I am falling. I'm not floating. I am falling. And the astronauts on the space shuttle are, in fact, falling. Constantly. I'll let you write that down. If you want. You